Morning. Today I wanted to talk a little bit about maintaining and operating resource efficient such as vineyards. It is a maintenance issue that's often overlooked, and it can provide a lot of savings to the grower as well as maintaining the yields in any season. So, what does it take to be resource efficient? It starts with a good system design, of course. You need an accurate and skilled person designing this system that will allow for a flexible operation. The system has to be properly installed, regularly maintained and evaluated, as well as some input from the grower that will find irrigation strategy, such as if you're deciding to do a full placement, deficit irrigation, such as sustained deficit or regulated deficit. Or if you're going to be irrigating the vineyard or the orchard homogeneously or using variable rate irrigation. This has to have accurate irrigation and scheduling and control, and with schedule and implementation feedback, which we can explain at a later date. So you have to have these components together: design, maintenance, as well as operations in our case. So, what is the most adequate irrigation method for the grapevine, since that's mostly what I work with? You have to be irrigating the vine, and you're going to be irrigating the vine by delivering water to the ground. So, root system of the mature grapevine consists of a woody root frame with smaller absorbing roots branching in multiple directions. But rootstocks might affect that. These roots will mine the soil horizontally and deeply. Uh, Vineyards thrive in soils with a good balance between water and air. We do not want saturated soils. Now, vineyards also do not enjoy soil compaction, water, and wet, dry cycles. We use low volume irrigation systems hand in hand with careful management and timing of amounts of irrigation and fertilizer. When you come to the design stage in vineyard irrigation, of course you have to have a preliminary site evaluation, such as do you have enough? Do you have the correct soil texture? What kind of variability you have? Is there a slope to the vineyard site? What direction is the slope facing? What kind of vine spacing and row orientation you will have? Trellis system has an effect in the site evaluation. Now, projected canopy size at full development. What kind of water will you be delivering? Of course, once you have these variables, you can define the water application rate in inches per hour and maximum irrigation depth in inches based on soil properties such as infiltration rate and water holding capacity, and of course, most importantly, crop evapotranspiration. The rule of thumb is to apply peak daily evapotranspiration, which is in inches per day, in a 16 to 20 hour set time maximum. We design these systems from downstream to upstream. For example, from the emitter by the vines to the submain to the laterals to the main line, flow meter, injection equipment, primary filters, and all the way down back to the pump. You need to also be able to calculate the flow and friction losses along the pipe system, size the various parts, capacity to ensure routine and maximum system load. You need to make sure that you're going to be irrigating this vineyard from the time you plant it, from the time of you're to be pulling a lot of yield. So you need to have some sort of flexibility in the operating of the system. You will have a range of operating conditions, and you need to be able to adjust the operation to various system loads. During its lifetime, it will be operated under different conditions. These of young vines are quite different, and these will increase with time. So the quantity and the pressure of the you might also have different elevations and distances from the pump supply. So you need to be able to vary the pressure that you deliver uh, to the different portions of your and blocks with different emitters. There might be soil differences. The quantity that you deliver to every block might be different, as well as the pressure. More often than not, we see different composite systems with different flow rates and pressures. Sometimes people will have drip and micro sprinklers and blocks right next to each other. You might have single lines or dual lines, alternating versus solid irrigation sets, etc. All these things will count in the flexibility of the operations of an irrigation system in a vineyard. Nobody's immune to it. Groundwater levels fluctuate, and they might decrease with time. And then as these, deplete with time, the pumps start wearing out. So the pressure of the system has to be managed, or pump need to be maintained. The second rule of thumb when you're looking at these things, when you're setting up these irrigation systems, resource efficiencies, the maximum amount of water you apply in inches has to be less than the water holding capacity of the soil. Although with micro irrigation, we might be tempted to micro flood these vineyards. Careful or cognizant of the water holding capacities for different soil types. Usually, this is the difference between the field capacity and the wilting point that we might set in these different soil types. Here's an idealized figure or table of water holding capacities in inches per feet. You can go from very coarse sands to pizza mucks. Most of our vineyards are in a medium texture to a moderately coarse texture soils. So our average water holding capacity is going to be about 1.5, 2 inches per foot. One thing I must point out that soil electrical conductivity, which can be measured proximally, is directly related to texture and water content, and you can relate this spatially over large acreages to what kind of these soils. This work we did years back, we identified that water content measured with proximal sensing over long distances and areas, and then this is really texture of the soils. Of course, after that you need to calculate some kind of maximum water depth for your irrigation. This is usually based on evapotranspiration. Different systems of irrigation that can be put up. You have surface irrigation, sprinkler, micro sprinkler, and finally drip irrigation. The efficiency of irrigation varies between 85 to 95%. When you're calculating maximum water depth of irrigation, we usually take the maximum daily ET multiplied by irrigation frequency and divide by the efficiency of application. In this example, we looked at a 3-day period where we had roughly about 0.6 inches over the course of the 3 days, divided by the efficiency, 85%. And this resulted in being about zero point 0.7 inches that has to be delivered in less than 24 hours in our specific case. Micro-irrigation systems, such as the systems we use in our vineyards, are usually designed for the lowest cost and at this lowest cost, they have to deliver the peak evapotranspiration of water needs in a 24-hour sets. But it's better if the system can deliver this in a 16 to a 20-hour set. Looking at this, you have different systems, you have different application rates in inches per hour. And if you look at the drip irrigation, they're delivering quite a low rate, so it can be a steady stream of water at a low rate coming into the vineyard. So, you have to match this to the soil-based calculation of maximum irrigation depth. When you look at this, the maximum depth of water to apply per irrigation is going to be related to the water holding capacity of the soil, the percent wetted area with the system you have in place, effect efficiency of application. The formula might look long, but it's quite straightforward. Here's a calculation example that we had from Napa County. A Matura Cabernet Sauvignon vineyard was spaced 5 by 6 on a VSP trellis with a single drip ascertained to be about 5 feet. It's about 70% is effective of 3.5 feet of root zone depth. The wetted area in this case was about 25%. It was a sandy loam site. The field capacity was 3.25 inches per feet. The wilting point was 1.679 inches. Total allowable was the difference between the field capacity minus permanent wilting point, 1.6 inches. Manageable allowable deficit in this case, in this type of soil, we set it at 50%. So 0.8 inches per foot. Then the maximum growth of irrigation depth to apply, then is applied missing variables filled in, and then you can also you can also convert this to gallons per plant as a volume using the formula DG max multiplied by the spacing, which is 5 by 6, multiplied by the constant of 0.623, and then you we're operating these systems, you have to be cognizant of the typical flow rates and pressures. Drip and micro sprinklers, they're delivering anywhere between 0.5. Operating pressures of these are between 20 to 35 psi. Micro irrigation emitters, they might require 7 to 12 psi. These are the emitters you have in the vineyards. Of course, any irrigation system will have a filtering system. They will require another 15 to 25 psi. Filters are a critical component of the irrigation system. They will require an additional 15 to 25 psi. If you're using a back flushing type filter, to 35 psi for them to operate. As you will see here, the flow meter, pressure regulator, manner. And then I cannot emphasize the importance of having a flow meter at least at one point. There are energy requirements for irrigation. It'll take about 1.37 horsepower per hour per acre foot. The pump must provide to lift 1 acre foot of water by 1 foot. Okay. Various fuel sources, electricity, natural gas, diesel, and propane, and the pump output, they will have different energy requirements. The sources of energy, also provide different energy units to lift the water. But electricity, it'll take about 1.55 kilowatt hours per acre foot per foot. A mature vineyard with a micro sprinkler versus drip irrigation. In this case, vineyard was using about 1.5 foot of water per season. It was a 40-acre set. We compared irrigation methods of micro sprinkler versus drip irrigation, 35 versus 25 psi at the pump outlet. The water left 100 feet from aquifer level to ground. Looking at this, total dynamic head changes with micro sprinkler or drip irrigation. Micro sprinkler requires a higher psi compared to drip irrigation. Total dynamic head is 180 feet versus 158 acre foot with a micro sprinkler is about 1.9 acre feet versus 1.7 acre feet with a drip irrigation. If you're using diesel to pump this water out, 1/10 of a gallon per acre foot per foot of lift, you assume an average price of diesel to be about $5 a gallon. It's quite substantial for a micro sprinkler. But if you were to change this to a drip irrigation, because you're delivering a less amount of water with a less dynamic head, the amount of cost that you're going to supply for diesel goes down quite a bit. Some recommendations: you need to evaluate the system at least every 2 to 3 years. Distribution uniformity and application rate changes over time. Okay, you need to know your system's application rate and distribution uniformity. These are key elements for scheduling irrigations. The time to run the system and water to be applied, the application rate, is a critical piece of information you need to have. The system needs to be monitored periodically to spot and correct problems. Check mainly the flow rate and pressure at critical points. High system efficiency in vineyards, especially in these days, requires significant efforts in routine maintenance. You need to check for leaks. Backflushing the filters is critical. You also need to periodically flush the main, sub-main, and laterals in that order. Chlorinating or cleaning for organic material, continuous 1 to 2 parts per million or periodically 10 to 50 parts per million, ensures that you do not have a growth. Sometimes acidifying the water is required to remove precipitates, and cleaning or replacing clog emitters and other components. Now, clogging is the main cause of poor system distribution uniformity. Emitter heads can get clogged. The filters themselves can get clogged, as well as emitters themselves. This is usually due to suspended material in irrigation water, chemical precipitation emitters, biological growth intrusion, and soil ingestion causes this. Irrigation system evaluation has objectives. You need to calculate the average application rate in inches per hour, system distribution uniformity in percent, and you identify the main problems and then correct them. You need to measure your flow rate and pressure. These are the things that you can measure in the field, and it's soft touch how to do this. Calculating distribution uniformity takes into account the average flow of the lowest 25% of the emitters measured divided by the average flow of all emitters. Example of distribution uniformity calculation in a vineyard. Usually in a block, 16 to 20 emitters will be measured for. You will pick average flow of the low forest emitters. The average flow of all emitters measured was 0.97 gallons per hour, divided by the 25% of the lowest emitters measured at 0.87. Distribution uniformity in this case is 90%, which is pretty good in this case. The types of clogging manageable through chemical injection can be due to slimy bacteria, iron manganese oxides, iron manganese sulfides, calcium magnesium carbonates, plant roots entry into the emitters. The action usually ends up with clogging the emitters. The remediation can be a chlorine injection, ozone, citric acid injection, sometimes herbicides to kill the plant roots that have come into the emitters. I'll show you an example of this, how we clean these and what can mean to you in terms of dollars. Usually when you're injecting this cleaning material, an average pipe velocity of 1 foot per second is assumed, and then you inject it, and then calculate the furthest distance, how long you have to run this system for. We evaluated a cleaning product and an organic product for distribution uniformity. We looked at a vineyard that was just installed, just a clean pipe. It was a Cabernet Sauvignon vineyard and a 110R rootstock. Identified distribution uniformity pre and post cleaning. Identify irrigation savings by fixing this distribution uniformity. This vineyard was irrigated with rainwater captured in a 20 acre-foot basin. In this case, our situation was at that point at 35 gallon per minute, designed to deliver 30 psi at each manifold. The irrigation system was a dual line hose. There were 4 half-gallon emitters per plant, and injection ports were at each manifold. Distribution uniformity was measured when irrigation started, and then it was cleaned up, constantly injected with a cleaning solution, and then it was then again measured in mid-August using the methods shown previously. So pre-cleaning, the pressure was around 2. Distribution uniformity was down to 0.7. It was 28, and distribution uniformity increased to 0.95. The way it worked was vineyard was irrigated for 1 hour. 2.5 liters of the cleaning product was injected via set overnight, and regular irrigation followed the following day. Uniformity is important because you can deliver the correct amount of water as well as the correct amount of fertilizer. And in this day, the vine mealybug infestations we're seeing, you can also deliver the correct amount of insecticide. Of course, this results in less pumping time as well as less water drawn. But we can put a value on this, and it's quite straightforward. I'll show you how to do this using this. The Excel calculator has some input data that's required from you, such as the surface area of the vineyard, spacing, emitter output, the elevation that the pump is drawing the water from, how far the water is traveling from the pump emitter, pump set point, and then head friction loss, which is in here as a formula. Baseline conditions, as I mentioned before cleaning, was 0.7. Distribution uniformity. Application rate was 0.94 gallons per hour. Enhanced conditions after cleaning was 0.95. Application rate increased to 0.15. Pressure head was 28. So these are the baseline and enhanced conditions, pre and post cleaning. You also need some other information. We measured the actual evapotranspiration in this vineyard using a surface renewal system. Surface renewal system, we got the season-long actual evaporation, 3 acre-inches per acre. And then the irrigation depth base, in this case, we can divide this by the base distribution uniformity to get the gross irrigation depth base. Now, here's a water savings calculator. The actual ET was a 19.38 depth irrigation. Pre-cleaning would be 27 acre-inches per acre. Gross irrigation depth enhanced would be 20 acre-inches per acre after cleaning. Okay, and this results in a 7.25 by acre-inches per acre of less water space. You don't have to pump as much water. Potential water cost savings, assuming a $600 per acre foot of water, is roughly around like $362 per acre. We were pumping this with an electric pump. Estimated energy use is of course going to depend on the total dynamic head. In this case, it was 142.5 feet. We were drawing it from 27 feet, 50 set point. Okay, the energy use prior to cleaning would have been 507 kilowatt hours per cleaning, would be 300 kilowatt hours per acre. That are substantial savings. I don't know too many people that are just irrigating 1 acre. This case is 133 kilowatt hours per acre. You can also convert greenhouse gas emission savings, how much less carbon you're emitting because you're pumping less water. Cleaning the system, then dosing at roughly at like 2 parts per million at each irrigation certainly helps. The cost of cleaning our solution is not that much compared to pumping and with a lot of electricity pumping time, it results in energy savings as well as less water pumped. System maintenance in micro irrigated systems is a must. You can maintain these systems close to design specifications if you are following a good schedule. This will result in applying the correct water and mineral nutrients, less pump hours, there's less energy cost, and less greenhouse gas emitted in this case, which can help you apply for sweep grants in this case. In your dosing with cleaning products can result in an increase in berry mass compared to no application of our cleaning product. This, of course, will result in an increased cluster mass compared to no cleaning product. And of course, you're going to get the correct yield because you're applying the correct. We have not seen any adverse effects in primary metabolites or any of the secondary metabolites using this approach because system is operating as it should. So that's what I wanted to talk about today. If you have like any questions, feel free to send me a message directly. I'll be more to answer them for you. Thank you and have a good day.